Welcome back to the next video, everybody. Today we're going to continue on proving the tetrahedral case of Theorem 9, or automorphic Langland's tunnel if you like. I love this proof. I really hope you enjoy it. Okay, so let's recall we're proving Theorem 9, which is kind of like a solvable n equals to Langland's reciprocity in the tetrahedral case. That is, in the case that we are given a representation rho from the Weil group of a number field F to GL2 of C, whose image in PGL2 of C, so mod scalars, is isomorphic to A4. Last video, we found the best candidate pi sub pseudo of rho for the pi of rho from Theorem 9. And now we just have to prove that pi pseudo of rho actually is the pi of rho from Theorem 9. Okay, more specifically, what do I have to prove? Well, let's give pi sub pseudo of rho local components pi sub b, where v runs over the places of f. Then for each v, I know from Theorem 5, for example, from a previous video, that pi sub b is pi sub b of rho prime sub b for some rho prime sub b of the local Weil group w sub f sub b to GL2 of c. Okay, what do I have to show then? I want to make sure things match up locally. I want to make sure rho prime sub b is rho sub b for almost every place b. That will be enough to show my representations are equal. Okay, now by construction, if a place w of e lies over a place v of f, the restriction of rho prime sub b to the smaller Weil group w sub e sub w and the restriction of rho sub b to w sub e sub w agree. Okay, what do I mean by this? Okay, w sub e sub w just lives here, so you can restrict this down. But remember, rho is just a representation on the Weil group w sub f. That can restrict down to a representation on w sub f sub b. And then that can further restrict down to a representation of w sub e sub w, which we might call rho sub v. Okay, or rho sub v restricted down at least. Okay, so what does this tell us? This tells us that if v splits completely in E, we're just done, because w sub e sub w is just isomorphic to w sub f sub v in this case. We talked about this already. And so without loss of generality, I can actually assume the extension E sub w over f sub v is cubic and unramified. That's the only other option from basic algebraic number theory. We also talked about that in a previous video. Okay, so from here on out, we have this extension is cubic and unramified. Great. Perfect. Now this extension is unramified, so it makes sense to talk about things like rho sub b of Frobenius at b, for Frobenius of b in the Galois group of E sub w over f sub b. Okay, and the other thing is I can diagonalize. I can just assume rho sub b of Frobenius at b is the diagonal matrix with entries, let's call them a sub b and b sub b. And I can also assume rho prime sub b is diagonal at Frobenius sub b with diagonal entries c sub b and d sub b, where all of the entries of these matrices are non-zero complex numbers because I don't want to kill the determinant on accident. Okay, the other thing though is this. Remember, these representations are unramified, so their images are determined by the images of Frobenius elements. And so these images here sort of determine the representation, okay? So to show rho prime sub b equals rho sub b, it suffices to show these matrices are conjugate, right? So that's all we have to do. So let's do that. Okay. Okay. Look, I already know by the discussion I just had with you that rho sub b and rho prime sub b restrict to the same thing on the local Weil group w sub e sub w. And in other words, or as a result, rather, rho sub b of Frobenius of b cubed is rho prime sub b of Frobenius of b cubed. This is because e sub w over f sub b is cubic. Okay. Well, that I know how to cube diagonal matrices all day. That tells me these two matrices are conjugate. The diagonal matrices with entries a sub b cubed and b sub b cubed and c sub b cubed and d sub b cubed are conjugate, because how do I cube diagonal matrices? I just cube their entries, right? Okay, perfect. So these are already conjugate. I'd like them to be conjugate without the cubes. Well, what does this say? This says that for some cube roots of unity, c and c prime, I guess, either c sub b is c a sub b and d sub b is c prime b sub b. So we're matching up here. Or we're matching up like this. So c sub b is c b sub b and d sub b is c prime a sub b. So one of those two things must be true or else these aren't conjugate. Okay. Now, what I'm going to do is under either assumption, I'm going to show that c prime must be c squared. Now, here's where you have to remember, how did we choose pi pseudo of rho? We chose it so that its central character was det rho, right? Well, that tells me that det rho prime sub v is det rho sub v, because the central character here is locally both det rho v and det rho prime v by construction. Go check Theorem 5, for example. Okay, so I already have the determinants of these guys are equal, and I have these matrices are conjugate when we cube the entries. Okay, we're getting somewhere. Well, if you go up here and play around and take determinants and use what you know, you just immediately see that C prime is 1. Well, another way of saying that, because C is a cube root of unity, is that C prime is C squared, but that's exactly what I wanted to show. Now that I know this, it suffices to show that C is 1, right? I mean, I'll let you check the details, but if C prime is C squared and C is 1, then these matrices are conjugate for sure. Okay, got it. So how do I do that? How do I show C is 1? I'm going to make a big assumption for the moment, and then later we'll have to tackle this claim. I'm going to assume that add compose rho prime sub v is add compose rho sub v, where add is the map that we talked about when we were talking about symmetric square lifting. It's the map from GL2C to GL3 of C. Okay, the kernel of add, though, is just the group of scalar matrices. That's an easy exercise. My assumption here tells me that rho sub v of Frobenius at V differs from rho prime sub v at Frobenius sub V by a non-zero scalar lambda. That's because the kernel of add is just scalars, right? In other words, for some non-zero scalar lambda, given this here, these matrices are conjugate. The diagonal matrix with entries CA sub v and C squared B sub v, and the diagonal matrix with diagonal entries lambda A sub b, lambda B sub b. These are already conjugate under this assumption that I'm making. Well, given what I want to show in this information here, is it not then just enough to show that lambda is 1? Should be, right? So I'm just going to show lambda is 1. Okay, but there are two possibilities if these are conjugate. Either lambda A sub b is just C A sub b, and lambda B sub b is C squared B sub b. Or lambda A sub b is C squared B sub b, and lambda B sub b is C A sub b. Let's tackle the first case. Okay, so it suffices to prove lambda is 1. Great. In the first case that I just got done outlining, where lambda A sub b is C A sub b and lambda B sub b is C squared B sub b, I claim lambda is 1 immediately. That's because lambda is both C and C squared, matching up coefficients, right? But C is a cube root of unity. The only cube root of unity C that equals its square is 1. So, but both of those are lambda, so lambda is 1. Great. How about the other possibility where lambda A sub b was C squared B sub b and lambda B sub b was C A sub b? I claim that immediately implies lambda squared is 1. That's a little exercise I'll leave for you, but I'll give you a hint. These relationships here tell you that A sub b is C squared B sub b over lambda, i.e. that it's lambda over C B sub b. Now use this equation to conclude lambda squared is 1. You can do this easily. Okay, great. So lambda is plus or minus 1 then, right? But it can't be minus 1 because the image of rho sub b of Frobenius at V, we already know is the matrix, diagonal matrix with entries A sub b, B sub b. But by what we're assuming here, that's just equal to the matrix with diagonal entries A sub b times the diagonal matrix with entries 1 C lambda in PGL2 of C. But the thing is, C lambda has order 6 as a complex number. So this guy has order 6 as a matrix. But remember, the image of Frobenius lives in A4 because we're in the tetrahedral case, and A4 doesn't have any elements of order 6. Contradiction. So lambda is not -1, it's 1. Okay, great. So if I believe that add of rho prime sub v equals add of rho sub v, I'm done. I've completed the entire tetrahedral case at least. So now I just have to prove this expression here, this equation here. Okay. So how do I do this? Well, the point is that add of rho from W sub f to GL3 of C is monomial because rho is. So by theorem 6 in a previous video with n equals 3, there's associated to this irreducible representation a cuspidal automorphic representation of GL3 of the Adele sub f. Let's denote that big pi sub 1. By symmetric square lifting, pi pseudo of rho has a lift to GL3 of A sub f as well, which we'll call pi star sub 1. Such that for almost all places V, the local Langlands class, I don't know, T sub big pi star sub 1 sub V equals add of the local Langlands class at V of pi pseudo of rho, which we know by definition is add of the local Langlands class T sub rho prime sub B. Okay, so I have all this. Okay, well, base changes are unique, right? It suffices to match these up. It suffices to show that these guys are isomorphic then. If these guys are isomorphic, then add of rho will be isomorphic to add of rho prime at each V. Okay, perfect. So how do I show these are isomorphic? Well, this guy right here, that it's an automorphic representation, and we know by symmetric square lifting that it's cuspidal automorphic if and only if pi pseudo of rho is not monomial. Okay, well, look, if pi pseudo of rho was equal to pi of rho prime for any irreducible two-dimensional rep, let alone any monomial representation, let's call it rho prime of W sub f, then by proposition 1 way back, rho would have to be rho prime. Well, that's not possible because rho is tetrahedral, not monomial. Okay, great. Well, then it can't be the case that pi star sub 1 is not cuspidal, so it must be cuspidal. Perfect. So this guy is cuspidal. Got it. All right. If you go and you revisit and look at the Rankin-Selberg theorem that I gave you, to finish the problem, I claim, and I'll leave this as an exercise for you, it suffices to prove the following. The Rankin-Selberg L function, L of S pi star sub 1 cross pi tilde sub 1 on GL3 cross GL3 has a pole at S equals 1, where the tilde here denotes the contragradient representation. And it's actually not too hard to show that. And I won't do it. It's done on CSS page 201. It's a somewhat tedious, but one page ultimately calculation. And I'm sure you can follow it pretty easily. But if you go through this proof, it's very beautiful. We used like automorphic induction. We used symmetric square lifting. We used base change. We used Rankin-Selberg stuff. We used all kinds of the theorems that we've been looking at over the previous videos. And like I said, the stuff that I'm holding out on you here isn't too hard to do. Okay, so we are done proving theorem 9 in the tetrahedral case. But there is one more case to take care of, which is the so-called octahedral case. And so I will begin looking at that next video, and I'll see you then, and thanks for watching.